in a positive way?
Negative.
No, ozone, right? We don't want to speed up the degradation of ozone.
Correct.
And we saw that example. I think let's see, I think we talked a little bit about this here. A more desirable one is in a catalytic converter in your car, where you convert some gases that are maybe not so good for the environment or yourself into things that are not a problem, right? That are not hazardous to your health or the environment. Let's see. So this would just be a fuel fragment. This is the same. What kind of reaction is this, by the way? Combustion. So you're looking at CH group mixed with oxygen, form CO2 and H2O in some particular amounts. These are all gases. So you use a catalyst to facilitate this reaction and speed it up, which of course is the point of this chapter, kinetics, right? We're looking at the rate of the reaction. Catalysts speed them up, but they're not used within it.
Right.
Okay? Are they part of our constant in the rate law? Yes, they are. That's exactly why I bring that up, right? And that's because, does that add to the rate of the reaction?
Right.
Yes, absolutely. So keep that in mind. We didn't work a lot with that, but I just wanted to remind you that was a couple weeks ago where we talked about that, and that's easy to forget, right? But since they're part, and one way to think about that is what's involved in speeding up a reaction. And a catalyst clearly is just like the amount of the reactants, right? So if I increase this, presumably that would increase the rate. You could increase so that you're dealing with K, you're going to increase the number of interactions, potentially the orientation. The catalyst presumably will do both, either speed that up and or orientate it properly, right? Like an enzyme in a biological system will orientate it properly. But it will also speed it up because it will bring them together. So a couple different things can happen.
From what I read earlier in the chapter, it seemed like they used catalysts along, like with, they combined it with the reactants. So you know how they write out the reactants, they write out the catalysts the same way.
That's right. In the rate law, if you increase the concentration of the catalyst, you will increase the rate of the reaction. The same way if you increase the reactants.
Right.
Right? Those are in concentrations.
Right.
How do you figure out how much it increases? Experimentally, right? Right? I double the amount of the reactant, or I double the amount of the catalyst.
Right.
What happens to the rate?
Right.
Those are found in what portion of our equation or our rate law? Those are the exponents, right? Okay. Just to wrap all the things that we've talked about and how catalysts fit into this. Okay, so let's briefly talk about different types of catalysts. This is relatively simple. We're just going to mention homogeneous and heterogeneous. And all that has to do with the state of the catalyst in regard to the state of the reactants. State meaning physical state, gas, liquid, solid. Okay, so a homogeneous catalyst, you have the phase state of the catalyst and the reactants the same. In this case, they're all gases, catalyst and the reactants.
Okay.
That's it. That's just a homogeneous catalyst. So what's a heterogeneous catalyst?
When they're not in the same.
When they're in different states. That's it. Nothing more than that. Okay. So our example of ozone being destroyed or facilitated, sped up by the chlorine that came out of the CFCs, if you recall that. This is in the gas state. The ozone is in the gas state. This would be an example of a homogeneous catalyst. Simply because of the phases that they're in, for no other reason. That's all the description is. Okay. Heterogeneous, you have something like this, where I have a solid, I have the different reactants, let's say in gas phase. They are now attracted to the solid, which then brings things together, allows them to interact and leave relatively easy. So it's just a way to, in this case, just what somebody mentioned over here, bring things together so you increase the what? Part of K. P and Z. Which one's P, which one's Z? You guys are on the right track, absolutely, but I'm trying to make sure that it's set in your head more comfortably. Which is P, which is Z?
C would be the E.
Collisions.
Right.
So this is going to increase the collisions or the number of opportunities that they interact with each other, right? Not necessarily will it orientate them, by just being in a different phase, but it will bring them together so that they're not free floating with a radius or with a distance between them this far apart, but maybe this far apart, which allows them to interact much easier, right? And that's, so this would be a heterogeneous catalyst. And this is something you find in a catalytic converter, by the way. Okay, so that's the difference between a heterogeneous and a homogeneous catalyst. Does that make sense? Just simply different phase between the reactants and the catalyst. Okay. So in this case, they're going to use a heterogeneous catalyst. You're simply going to have a solid matrix of something that allows this thing to bind, this to bind, that keeps them in closer proximity where they eventually will interact, and then they'll leave as this. So when you're talking about hydrogenation, you're really talking about a C double bond here or a C triple bond, and you're adding hydrogen. So let's say I have C triple bond, C, H, H. This is a triple bond if you do the Lewis structure, simply because how many bonds should you have to carbon? 4. So if I have only one hydrogen to each, then I need the other 3 bonds between them. 1, 2, 3, 4, 1, 2, 3, 4. Hydrogenation, add the H2, 1 H comes here, 1 H goes there for the carbons. What that does is that breaks one of these bonds and fulfills the structure of carbons, right, where you have 4 bonds still. And then I do that again, which is what I do here. I just add another H2, 1 H goes here, 1 H goes there, that breaks another bond, and ultimately I now have this structure here. And that's all that is. Does that make sense? Okay, so how do I get the hydrogens on here? Of course, they could interact in their gas phase and eventually come in contact with each other. But if I have a matrix and they come to the matrix, then they could bind closer to each other and facilitate that reaction, make it, speed it up, make it go faster. Okay, and that's all that's happening here. And I think we'll see, is that what this is? Yeah, that's basically what this is. So they're using different terms here, so let's make sure we're clear. That's an ethane. We're not, actually you guys, some of you came from my class last semester in 101, so we did talk a little bit about organic chemistry labeling. In this case, it will actually help, right? What's the difference between ane, and ine?
The amount of the bonds.
Bonds, right?
Right.
Ane is single bond,
One.
carbon.
One.
Ene is double bond.
Right.
Ine, Y-N-E, triple bond. So that's what you're seeing here. So that ethene is a double bond, which is this right here. Add the hydrogen, hydrogen's diatomic, that's the H2. And then I hydrogenate them, and then I simply get rid of that. I now have the H forming ethane, right? So it goes ethene to ethane. And so that's what's happening here. I have my matrix. You absorb these molecules that are in the air, ethane and hydrogen, come over here, they diffuse, they're close to each other. By the way, these someone asked me about this, and maybe I should bring this up since I just recall it. One of you guys asked me, I can't remember, it might have been Dieter. So they don't just stick there in some strict, locked-in position, obviously. This is a weaker, looser interaction. You could think of it as an intermolecular type of interaction, right? Not a chemical bond. So there is some movement that's allowed by this interaction. So you have to find the proper piece or catalyst that's going to allow for certain things to bind to it, but not bind too tightly, right? I don't want it to be too rigid because they need to interact with each other. They're not going to drop right next to each other. So I have some matrix that allows it to get close to each other, allows for some movement, as we're called diffusion here, properly orientate, form from your ethene to your ethane, and then that ethane can leave, called desorption. And this is the progression: absorption, diffusion, reaction, desorption. Of course, it doesn't have to go exactly in that same pattern, depending on what you're mixing with what, but those are the general components to what's going to happen by having that heterogeneous catalyst. Okay. Any questions on that? Go ahead. Question? Okay. So that leads us to our final type of catalyst, which is an enzyme that's in a biological system. And I think we've talked a little bit about this. I'll let you read that, nothing special there. Enzymes generally have a active site, which I know we've talked about. In the active site, it's also stereospecific, meaning that the 3 dimension of it is important, which is why the stereochemistry on the molecules are important. If I have, let's say, even a hydroxyl group sticking off the wrong position, wrong side, it may not properly fit into the enzyme. Okay, and you'll find more about that in OChem and biochem. But I have an active site. I have a substrate. Either one thing can bind to separate, which is, I think, the example we'll give you. But you could have 2 things bind, 2 ligands bind, and then position themselves to interact in an appropriate way. In other words, properly orientate them, and then release it once it's done. So it could go both directions. You could have different types of things. I think we'll only show one because it's a simpler one, where you have an enzyme, you have a substrate. That substrate comes in, fits in, it adjusts, it separates it, and then you leave. But in between, you have a transition state, which is the ES state. And that would be where did you see the transition state kind of thing happen? Earlier in this chapter, we talked about transition states. Where did you see that? It was on a chart, right? The activation energy, absolutely. It was the top of the activation energy. That's where your transition state is. Okay, so keeping all these things in mind, what we learned earlier, to how they now apply. So here's a simple little example here. If I take it in an equation, I have 2 steps. What are those steps? How did we define those when we started talking about determining the exponent and the actual reaction rate? Elementary steps, and these are all based off of a mechanism. So this is the mechanism that we're demonstrating for an enzyme binding to a substrate and producing a product. Demonstrated in 2 steps. You have the enzyme and the substrate binding, forming the transition state, the ES. Right? Then the ES, after it overcomes, you get enough activation energy. Now it goes into the enzyme coming back out, and the product, the new thing, which could be 2 things, or 2 things became 1. And we're saying the first one is the fast step, which is in an equilibrium going back and forth. That's because sometimes they get up, they're trying to get up to the activation energy. Not everything has enough energy to get to that point, so it comes back down. Right. When they can transition above it, then you get the ES state, which then breaks it down into E and P, and that's the slow rate determining step. Right. So if I was looking at the elementary reaction and I wanted to figure out the rate law, which one would I use? The first or the second part of this mechanism? The second, absolutely, right? That then I would determine whether what state it was. I would match based on data. I would match that data to this, and I should see something that says E to the first and P to the first based on that. Right. Okay. So here's a nice little description of just a substrate in one piece binding into the active site of the enzyme. It now overcomes enough energy to get to the place where I'm at the transition state, the enzyme substrate complex, which is now connected. These things separate and they come off as products, and I reform my original enzyme. Okay. So here's my substrate S plus E going, this should be in equilibrium as illustrated up there, going back and forth here. Enough energy comes, I get to this stage, which now allows it to move forward on the bottom half here, ES, going to my substrate and my enzyme here left over. Is that okay? So all we're doing really is just looking at speeding up the reactions, right? In this case. Once again, I could have something here. Let's say I start this. These are my substrates, which also can be called ligands. And here's my enzyme. They bind here. They form into this enzyme substrate complex, and then they release this as a product. So you can think of this going backwards as well in a different type of reaction. It's not always just going that direction, right? That's what an enzyme will do. It will bring things together a lot of times, more often than it will separate them actually. Okay.
Correlating that with the process of the RNA when it's bringing in the
so you're talking about translation,
right?
So you want to go from DNA to RNA, or from RNA to protein.
Right.
That's the translation. Transcription is the DNA to RNA. Which step?
The translation. No, transcription when it's actually creating the protein itself.
Okay, so you're making the transcript, which
Right.
is the RNA, or you're taking the RNA as a template to make protein.
That one.
Okay, so that's the
template to make
translation.
protein. Okay, translation.
Yeah. And each one of those have a lot of enzymes. And in fact, just interestingly, back when I went to school and I sit in these kind of classes, they didn't know this, but now RNAs also form enzymes. So RNases,
Right.
right? Back then that wasn't known. And
Yeah.
also you have your mature and your splicing and all this, so you
Right.
get all these different transcripts from that. So there are a whole bunch of different things going on now.
Introns, right, yeah.
But those all have enzymes. So enzymes do not necessarily have to be a protein, in other words.
Right.
RNA can also be an enzyme, RNases and things like that. We'll slice up RNA and other things. So yeah, enzymes play a prominent role. It used to be thought of only as active proteins.
Right.
Right. Okay, so here I have sucrose, and this needs to be broken up into glucose and fructose, and it's separated at this stage here in order to get both the glucose and the fructose. And this is done by an enzyme. The enzyme is sucrase, and that should be here, sucrase. So I think in your book you probably have a picture of something that looked like the last thing, an enzyme, and it has an active site. This thing fits in there, allows for this to be separated, and then these leave as the products, and your enzyme sucrase reforms. Now, in a biochem classes, you learn more about the mechanisms of OChem. You have SN1, SN2 mechanisms. You'll actually see where these positions are literally binding onto the enzyme. They're making connections. And then how those connections allow for this separation or formation, depending on which direction you're going.
Sure.
And these factor throughout everything we do, our cells do in our body. So this is just separating glucose and fructose from sucrose. Now I want to break down glucose. What procedures do I go through? The first thing I have to do is what? With the glucose? Break it into
Water.
two,
Yeah, add water.
right?
Hydrolysis.
Hydrolysis. Does that take enzymes?
Absolutely.
Yes. It speeds it up. Then it goes to the intermediate interaction, right, where it does a couple things, and then you get into the citric acid cycle. I don't know what they call it now, TCA or the Krebs cycle, I think
Krebs
they used to
cycle,
call
yeah.
it. Is that what you guys call it now, Krebs cycle?
Yeah.
Krebs cycle. And you have all of these different things that are occurring, 3-carbon being broken down to 2-carbon, you're losing
Pyruvate
CO2, you're gaining ATPs and NADHs and all kinds of things, right? You have 1, 2, 3, 4, 5. Every single one of those stages has a different enzyme that helps facilitate that reaction, just to put that in.
FAD or
That whole cycle.
FAD and NADH.
So what are those? So when you see NADH and
Those are the
FADH2s,
enzymes,
those
right?
formations, what are those?
Those are enzymes, no?
Are those enzymes? Are they
They're the one that carries them.
coenzymes?
Coenzymes, yes.
A little bit
Yes.
different, right?
Yes.
So they attach and add to
Right.
the enzyme to speed up the reaction, and these are all things you'll get
Take the
in a
electrons
lot
out,
more
right.
detail as you get further in chemistry and like into biochemistry, just to put that in perspective.
Right.
Right, but these are all the different things going on. So at this stage, we're just saying, hey, look, an enzyme, throw a couple things in there, it makes things closer, speeds up the reaction, no big deal.
Right.
As you go through OChem, you'll figure out the specific mechanisms to how those do it, and as you get into biochem, you'll see how they place within the enzyme based on what we know from three-dimensional structures and things like that. Okay, and with that, I think that ends our discussion on
You see when the bind is
kinetics.
it?
Huh?
When the bind on the substrate would be into the active site would be through the ligands?
The ligands
The
are
ligands?
the substrates.
Oh, okay, that's
We'll talk more on Thursday, or maybe, yeah, we'll talk more on Thursday. We'll see where we get. And then Dieter, I saw you had a question, you had your hand up before we leave this section. Did you still have something to add? Or- Okay. Good enough. I didn't want to leave you hanging, but I wanted to finish the point at that moment. Okay, with that being said, the exam somebody just asked about, we'll talk more about it on Thursday, but it's going to be on both chapters 14 and 15. 14, you just finished your first chapter. By the way, the chapters are much longer. I mentioned this at the start of this class as
Yeah.
what you saw in Chem 101, right?
Right.
So you're going to have less chapters overall. You just finished your first chapter in 102, so you're on your way. Now we're going to get into a section that's going to be pretty much dominating the next several weeks, maybe even month or two
Oh, wow.
in this class in different ways. And that's equilibriums, chemical equilibrium, something you've heard about in 101. We've talked about it in the context of things like acids and bases, weak acids, weak bases. That's where you saw the double arrow equilibrium. I've brought it up multiple times if you've taken me in 101, and that had to do a lot with
the going back. Yeah, the Chapman equation.
I have a rate going one way and a rate coming back the other way, and they're equal, not concentrations. I also have mentioned in past lectures, for those of you that had me, and I'm assuming that whoever else you had, concentrations are not necessarily the same.
Right.
I start with a certain amount, I end with a different amount here. Most of the things we looked at, I said I have 95% this and 5% that. Do you remember those things where I'd say, for example, let's put it in like HC2H3O2, and I'm going to mix that. This is an acid, a weak acid. I'll mix that with a weak base. Let's say NH3, and I'll get NH4 plus C2H3O2 minus, and this will be in an equilibrium. And I used to say, well, you'll have the majority of this, so let's say 97% of this will still be here, and then you'll have 3% of this once it reaches its equilibrium, or you have a certain amount going this way and a certain other amount coming back, a dynamic equilibrium, so that the amounts of these never stop changing at equilibrium. Even though you're still converting this way, you're converting at the same rate this way, which is why we talked about rates first.
That's the
The
same
rate
thing
of the
with
reactions are the same.
in the blood, right? Or the bicarbonate as well?
No, this is acetate, but yes, that
Bicarbonate
does
does
happen with
that.
bicarbonate, but I don't want to get too deep because I'm going to let somebody else introduce this. What I want to say is, as we move forward and we discuss this interaction, when I would mention these things, you guys are going to be able to figure out what the actual percentages are or the amounts. Okay, and that's where I used to just have to rely on when I would say, you're going to have about 97 or 95% this, and it's going to be about 5% that. We're going to actually learn how to figure those out eventually. But to introduce the topic of this kind of thing in this equilibrium, I'm going to bring up Nathan and let him go ahead and introduce it to you. So you have a guest lecturer, Nathan? Right? This one goes this way. All right. What is that one?
Hold the clicker, yeah. Okay, so like he said, we're going to be going over equilibrium today, and let's try to make this as smooth as possible. I've tutored like 50% of you already, so I'm just tutoring the other 50% now. Okay, so we're going to demystify the double arrow, essentially, right? It's when we're going to quantify this in a meaningful way. How do I get the light? Do I get the laser?
The top, very top. And sometimes it's faded, so you might struggle if it's not.
Yeah, okay. Just around this region, we're going to start quantifying things. But my job today would be to introduce it to you guys to equilibrium and what that means. So starting off, we'll start with chemical equilibrium. We'll define it. We'll do it as a stepwise process, and it'll really be quite clear. Almost too simple, it will seem. We're going to introduce another K value. You're going to have about like 17 different K values to keep track of. So yeah, just get used to that. K's are a thing, yeah. And calculating Kc. So you guys, these are things that you guys have actually been introduced to already in your lab.
Yeah.
You guys have been doing this already. You just didn't know what it was called. So we're going to introduce the law of mass action, hopefully today. What time do we have till? 2025? We're going to do it. We're going to complete the whole chapter today. Yeah, let's go. So you're, okay, we're going to go over a couple other constants, but yeah, so I'll let Fenton go more into detail with this guy, but let's get started. So just go right, you said, right? Or go down? What? Press the forward button.
That was quick.
Yeah, right.
That was fast, man.
Bottom, right? Yeah.
Wow. Okay, you're ready.
Cool. All right, cool. Hiccup at first. So,
That's it.
yeah, chemical equilibrium. We're going to talk about reversible reactions. This is what you're used to seeing, right? So A and B form C and D. But what if it's energetically favorable to go the reverse direction, right? This is what we're talking about. This is the reverse reaction. And the way we indicate that that's a possibility, we include a double arrow. And that's what you guys are seeing. So you're going to start using it now from this point on. So that's the double arrow. Yeah, these reactions seem to stop before they go to completion. And this has been kind of weird, right? So Fenton would bring up the fact that the rate of the forward reaction equals the rate of the reverse reaction. And that can seem like, okay, I get that. but I want you to think about it in a different way. It has nothing to do with concentration at all, like you just said. Imagine if one person came in the door and one person came out the door, right? The rates are the same, right? People are coming in at the same rate they're coming out. But that doesn't mean that the concentrations. There are certainly more people outside of this classroom than there are inside this classroom currently, right?
Yeah.
All we're saying is at the rate that one person's leaving, one person's coming in.
Right.
That's all that means. So yeah, so what we're going to talk about is how to quantify that. So yeah, so once we, there's going to be a stepwise process. Let's see this guy that way. Yeah, so starting out, all we're going to have is reactants, right? A high concentration of reactions. But we're not going to have any reaction going in the reverse direction because we've yet to make any products. That's all that means. So, step 2, we're going to start to lose reactants because we're using them up, we're wasting that fuel, and we're starting to build on our product side. Yep, so we start to slow down on the reactant side and speed up slowly on the product side. The third step, we're going to see, yep, so it's going to go down even further. Not to depletion, but it's slowing down. And at that point, it's slowing down. The other side starts to speed up because we're building up that product. If we do that in such a way, we're going to reach an equilibrium in which both are going in the same direction. So notice, it's a dynamic process. These continue to go in both directions. One person's coming in the door and the other person's leaving. It's not stopping. The concentrations are constant, but they're moving from forward and backwards at the same rate. That's all that means, yeah. Equilibrium.
That doesn't happen with the sodium-potassium pump, right?
With the sodium-potassium pump, no, that has more to do with diffusion, yeah, and so on, yeah. But you did bring up the bicarbonate system, and yeah, well, you can go. You'll probably understand it a lot better now, actually, after this lecture, yeah. So,
Right.
yeah. So, what we see here is a graph that demonstrates the concentrations of the different reactants and products, and as we see, we get this asymptote, almost looking kind of thing, right?
Right.
In which the concentrations are constant, right? And the rates at which of the reverse reaction increases as time goes on, which makes sense, right? As the
Products.
Yeah, as we start the clock, our rate of the reverse reaction is only going to get faster, up to a certain point, though. Yeah. And once we reach that asymptote, they both reach the same point, and we're going to be at an equilibrium. Cool. So the rate of the forward reaction, we start to slow down. We see a negative slope right there. Boom, boom. It continues to get more and more closer to a line. And as at that point, we start to increase that slope going in the reverse direction. This guy increases. And there we go. We've now reached equilibrium. At equilibrium, there are no further changes in the concentration in the reactants or products. And I can't really stress that enough, right? Right? So you guys are going to be dealing with this for the rest of the semester. In fact, I'd probably argue this is probably the most important chapter as your foundation. So yeah, treat this with the utmost importance if you can. Is this going to be on their next exam as well, or is it? They have 14 and 15, huh? Holy cow! Wow. Okay. Yeah. Okay. Equilibrium. Yeah. So mixture of reactants and products is present. Changes. Yeah. So these are all things that we've stated already, right? Yeah. So constant. Yeah. So at equilibrium, our concentrations are going to stay constant. That's probably been said 30 times already, right? It's the rates are equal, the concentrations are constant, right? That's what it's. But that does not necessarily mean the concentrations are the same on both sides. It just means that they're going in the same way, yeah. So how do we quantify that, right? So this is what we stated. We said that there is a dynamic equilibrium, meaning that it's moving forward and it's moving backwards. It doesn't just stop, right? And that means it's really delicate as well. So if we were to alter or add a stress to one side, it would fluctuate in one direction, right? So it's a very delicate thing we're talking about here. Yeah. We can control that equilibrium, right? By adjusting the left or right part of the reaction, we can alter the equilibrium in a way that we want. So, yeah. So we can shift. If we increase the concentration on the left, what you'll see later is that the reaction will propel to the right.
What are some ways to do that?
Yeah, you guys have been introduced to that, yeah.
Raising temperature.
Yeah, raising temperature, yeah. Has anybody had any experience with equilibrium or anything? Yeah. Mhm. Yeah.
But what are
Increasing the concentration.
Intuitively, right? Yeah.
Mhm.
Yeah.
Catalysts.
Increasing concentration of reactants.
Yeah.
volume? So if I have gases, volume could play a role. So
Right.
increase, right?
Yeah.
What about other things? What are we talking about when we're talking about the rates here? So let's preface this. This is all in some condition, right?
Mhm.
And right here, A going to B, B going back to A under some condition. What is wrapped up in those conditions? What do we call them? Constants.
Right.
What's in the constant? Temperature, activation energy, orientation. If I change any of those, I'm now shifting to favor one over the other more or less. So if the temperature is playing, if I increase the temperature, and that increases A wanting to go to B, I now shift this equilibrium so that I have a greater concentration of B than I did A, right? In fact, when you go back to every one of your chemical equations and reactions that you've learned up to now, we always had one single arrow going one way.
Right.
Do you really think that everything goes 100% one way in all of those things?
No.
No. Almost every one of them have some tail end extra going back or not going all the way. And we're going to learn more about that later on after we've established what's happening in the equilibrium. But the reason we went over rates prior to equilibrium is for that reason, so you understood what's causing a rate to speed up or slow down. And that is what establishes those conditions, establish that equilibrium. And when I make adjustments to K or anything else, I'm now going to shift that equilibrium one way or another depending on which way I'm favoring it. So if I have an activation energy that takes A to B up here and I shift it down, that's going to make this rate go faster than the current equilibrium rate, which is going to shift more of this way and reestablish a new equilibrium. So everything that you've learned in that first chapter was setting you up so that when we got here, you would have a better sense of why we're here and how to make adjustments to it and why adjustments are being made.
Yeah. Yeah. Perfect. Yeah. Yeah. So yeah, again, this is reiterating what we said, right? So yeah, when the rates are equal, we've reached an equilibrium. Yeah. So yeah. Okay. The equilibrium constant is really the meat and potatoes of this. Yeah. So another constant, and what does this constant represent, right? So constants like that you learned before in the rate law, you learned that they represented the activation energy, and they told you a lot about what that reaction would do, right? How fast it would be, right?
Right.
In this particular case, our constant's going to tell us how much of the products do I have and how much of the reactants do I have at equilibrium, right? So once we've reached equilibrium, how much am I expected to find of the products and how much am I expected to find of the reactants? And this K constant is going to tell us what that ratio is, essentially. So let's see. So we're going to consider a generic equilibrium equation, right? Where the coefficients are the lowercase variables that you see there. And we're going to introduce, let's see, this guy here, the law of mass action, right? Which is something you guys might see. It's a big vocab word. But essentially, what's happening is, notice it's the molar concentrations of the products divided by the molar concentrations of the reactants. And the stoichiometric coefficients that you found on this previous slide are the exponents that you see in the order here. So that's entirely different than what you learned in rates, right? You learned that you can't get it from the reaction, right? Which is why this can be confusing, right? So in this particular case, you need a balanced chemical equation in order to have a proper K expression. So I can't emphasize that enough. You need to have a balanced chemical equation in order to get any of this correct.
Right.
To understand it, yeah. So yeah, products over reactants. So if you were to think about that, if I had a very, very large K value, let's say 10 to the 14, would that represent having more products or more reactants?
More products?
More products, right?
Right.
Because that would mean my denominator is very small, right?
Exactly.
In the other direction, if I had a very small K value, 10 to the minus 10,
Yeah, more reactants.
it would mean that this reaction doesn't really go and doesn't propel to the right. That's what this means, yeah. So molar concentrations of the reactant of products over reactants, and their squares or their powers are going to be their coefficients. So,
Right.
Let me ask real quick. How do you guys view kinetic constants versus equilibrium constants? How are they different? So you don't have to say anything. I want you to just think about that. What makes one a certain thing, and what does it indicate, and what makes the other a certain constant, and what does it indicate? Just because they're called constants in Ks,
Yeah.
they have completely different meanings. And understanding the meaning will make it easier to understand which one to use when and why and where. So just think about that. In other words, you don't have activation energy wrapped up in the constant for an equilibrium, right? You only have concentration. So all the K of the equilibrium constant is looking at are which way is the equilibrium favoring. It's
Okay.
simply that.
Or the other one is the rate?
Whereas you look at rates, and there's a whole bunch of stuff wrapped up that we unpack out of
Right.
that. So the Ks mean two completely different things, so keep that in mind.
Right.
And then think about why. So if you're looking at equilibrium, or you're thinking about kinetics. Now, the kinetics of the kinetic constant does play a role because it can influence the direction that's happening in an equilibrium.
Right.
But the equilibrium constant itself is just simply the concentrations of the reactants and products.
Okay.
Right, so keep that in mind in the dynamic.
Yeah. So in this particular case, our K value is independent of the variables that were in our rate constant, right? Like temperature and, the other constants like R, and activation.
But if I did change that, what would happen to the equilibrium constant?
Exactly, yeah.
Then it would change because the amount of the reactant or the product would change.
Right.
So keep how that dynamic works.
That one affects this one.
Yeah, right.
One can influence the other.
There's a relationship with them, essentially. Right? So yeah, what this particular slide says is that you need a balanced chemical equation before we can even start this, right? The coefficients that in our chemical equation become the powers in our K expression for equilibrium. Yeah. For example, if we have a chemical equation like this, all of the coefficients here are going to become the powers when we're solving for K. Yeah.
Okay.
Does this mean that this equation is always going to be the slow step, or is this the actual overall reaction?
This is overall reaction, molecular equation. Yeah, yeah.
So then the
Yeah.
overall is basically the same as the slow step, right? Is that right?
Yeah,
I think you might be confusing this with an elementary reaction,
Right.
which this is not the case. Yeah, yeah.
This is exactly what I was just talking about, is identifying what K you're looking at.
Yeah,
Right?
yeah. Different K. Yeah, this is
Different K, which is really, really important. What you're saying is exactly what I was leading you away from, which is
Dang it, dude.
I baited you backwards. I baited you the other
There
way.
is some connection, but you're not familiar with that
Saying not to
connection
eat the
because this is- that connection here, this is just the reactants and the products. This has nothing to do with
Don't
the
do it.
effect
Don't do it.
of
Don't do
the
that. And then I don't.
relationship of the rate. The rate is broken up into
I was like,
mechanisms
do it,
and
do
different
it.
elementary steps. This is simply the products of the reactants of an overall equation. So
Same
you're
way
looking
like
at the
that.
overall equation
When he was saying
independent
about
of the
this
steps
today, he
to
was
see
staring
which
at me,
way
so I'm
it's
like,
favoring.
What? Oh,
Oh,
yeah.
That's why we have two different.
Yes.
Yes.
Yes, it's different, absolutely.
It'll be a little more apparent right now because when you're writing this K constant, so we don't mix it up with other K, we're going to have a subscript that relates to the K. So in this particular case, what should be presented here, there should be a Kc here. K sub C would indicate
Constant.
that it's the
Constant.
constant related to the concentrations.
Right.
Yeah. So then, yeah, if it's a Kp, it's related to pressures and so on, right? Ka, which you guys were exposed to, was the concentrations of acids in particular and so on, right?
Completely different from the rate.
Yeah, we're not talking about this entirely different K. Yeah, yeah. Good question, yeah. So yeah, notice that in this particular case, the coefficients of N2O5, we have it there in the denominator because it's products over reactants, and there's a power of 2.
Yeah.
And the 4 corresponding to the NO2 and so on. Cool. So note that the coefficients become the exponents and the equilibrium constant. Yeah, and here is like we said, right? So in order to avoid confusion, we're going to use that Kc there to indicate that, hey, I'm making an expression for the concentrations. I'm not talking about the Arrhenius equation. Yeah.
Is there a difference because in lab today we did KEQ? Is there a difference between KEQ
Equilibrium.
and KC?
KEQ and Kc should be the same thing, yeah. Should be, yeah. Yeah. We're going to go into some different types, yeah. Yeah, so this is,
Can you
yeah.
use without units because they cancel out?
Yeah, exactly, yeah. Yeah.
Can you explain why the coefficients are the exponents again?
Yeah, so then, so it's gonna, we'll go back to that guy. So what does that mean, right? So these are like molar ratios, right? Are they not? So then if I were to, would you agree that if I were to increase the amount of NO2, like the rate of it would be, there would be a 4 times greater influence than there would be of oxygen in that case, right?
Right.
Because it's just a molar ratio perspective, essentially. The weight of NO2 is very high,
Exactly.
essentially, because of the molar ratio. So we have to treat it accordingly with that power that you see there, yeah. So yeah, it's just molar ratios, essentially, yeah.
Yeah, there are four NO2s. So NO2 times NO2 times NO2
So what
times
did you
NO2.
use for KC?
Yeah. I'm sorry.
So the units of KC are, there's
Yeah,
just
they're going to be
one.
unitless as well. Yeah, there should be a slide that'll tell you that it's going to be unitless as well. Yeah, I think that we're going to go into how you can alter a KC as well, and I think that'll make it very clear as to why they're powers. Yeah, so note the coefficients. Go back. Yeah, there it is. It is common to
Just come into practice to write.
eliminate all of the units for K, which is entirely different than the rate constant that we talked about, right? In which you need to be kind of aware of those, right? Yeah. Yeah. Cool. As an example, I'd like you guys to take a minute to write the K expression for this guy. Yeah. Cool. I think you guys probably all saw it immediately and knew how to say it, right?
Right.
So in this particular case, we're going to do products over reactants. So our K expression should show that, right? Should be our NH3, H2O, and the coefficient of NH3 ammonia in this case is 2. So we put as a 2 as a power, and so on. So, yeah. Is that clear for everybody, right?
Yeah.
Products over reactants, right? Which is interesting, right? Because if this is a reversible reaction, right? Wouldn't you agree that if I was going the other direction, that
The reaction
these would be the
top.
products, right? Yeah. So,
Yeah.
so the perspective at which you're talking about it is really important. In this context, I'm saying I'm going this way, and these are my products. Yeah. So yeah, keep track of the at what perspective am I looking at this reaction, right? So yeah. Significance of it. Yeah. It's like what we said, right? The significance. We're going to get a number out of this. It's unitless. It's just a number that tells us the ratio of the concentrations. So like I said, if you see a large K value, right? A K value that's much greater than 1, it means that your favorite, like an example, like 1.9 times 10 to the 19, that would mean that you're favoring what? The products, right? The products concentration is much greater than that of the reactants. And I think that you said that we're going to choose a 10 as your value, right?
Yeah, and the one thing I just want to make sure you guys are aware of, you're talking here about the concentration of the products being more. So remember, you see that sideboard here. So if you look at something here where you have a KC greater than, as we're saying 1, let's say greater than 10, then would you expect this to exist, or what would happen with these numbers? They'd flip, absolutely. Right? You're only talking about the amounts of one side versus the other.
Right.
And if the K for the
Is higher.
equilibrium constant is greater,
Then-
is higher, then you're going to favor this. This is going to have much more than this.
Concentration.
What happens if they're about equal?
You got it, 50-50.
Yeah, you have, so if this is around 1, anywhere between 10 and say minus 10, somewhere in there, then this is about equal.
Right.
So now the equilibrium has about an equal amount on each side, right? And that's all it's telling you. That's all K is the concentration of the products over the reactants. So if you have a high number, you're favoring the products. If you have a low number, you're favoring the reactants. If you have something that's similar, then you're at the equal amount at the equilibrium. But that's only depends on what the K is. And that's all the K is representing.
That's a pretty rare case too, yeah, that seeing nearly 1 or 10, right? It's like, for the most part, when you get into acids and so on, like Fenton said before, weak acids, generally they're gonna have what, a very small K or a very big K? Small K, right? Yeah, because we said that, well, they only disassociate 97%, or 3% rather, right?
Yeah.
So then, yeah, you would expect your denominator to be huge relative to your numerator, right? Yeah.
What's dictating that? Why, in this case, are the products being favored? What's actually happening in the container or the test tube or whatever else? I have H2Br2. I start with that. I develop this equilibrium that forms 2HBr. What's driving that?
The electrons?
One way or another.
Because the electrons transfer?
Activation energy for both, maybe?
Right.
Not just one.
Yeah. Yeah.
Temperature. Orientation. So does the orientation necessarily matter for the right side going to the left? Does it matter more for the left side going to the right? Right? So if I look at the kinetics of one direction versus the kinetics of the other direction. So if I make a change to one or the other, how would that affect this? Would I increase one side or decrease the other side, or what would happen? If I change the K of kinetics, and that's what leads to this. So I have an interesting thing here, right? I have something that wants to go one way and something that wants to go another way, and what drives that? So there's a competition a lot of times too, right? There's a competition for the H. If I look at it that way, my hydrogens here are competing with bromine, and they're also competing with other hydrogens. And the ease of them going from one way or out competing the other way depends on the conditions, which are wrapped up in the kinetics constant and the rate. So you have to think about this representation and discussion is very, very simple. But you have to keep it in the context of what you know and why these things are happening. It's not just about, okay, this is high, therefore this. Yeah, that might help you pass an exam, but it won't help you understand what's actually happening, which is how you should be viewing
Is
this.
what I'm writing, right?
So for this case, here, we're only looking at concentration, so we could just say
I'm
basically,
saying my K is so
Like
big,
this value of
that
KC,
means
it's just the concentrations of the
The
reactants
larger
it had to
and
be
the
very
products that are
small
affecting
number.
this rate, right? For KC.
You're saying that at whatever the conditions of this rate going one way and the other, this is the result of that.
Just based on concentration.
Just based on concentrations, it's clear that the rate going left to right is much, much more than the rate going from right to left in terms of the overall amounts that you're gonna have on one side or the other. So this is gonna favor the product over the reactants based on the rates of both. Now, if I change some conditions, I might be able to switch that. Or if I add some external something to it, which would then change the conditions. For example, what if I added more, what if I had this, I have a certain concentration of hydrogen and a certain concentration of bromine, and then as a result of putting them together, I end up with this equilibrium. So now I have a certain concentration of this, this, and this after the equilibrium's developed. Okay, over time, because this is the time thing, right? Initially, I only have these two things, which is why they're on the left side. Over some time frame, I now have this equilibrium that has formed. Let's say 5 minutes has now gone by, and now I have this here. What if I just add some more HBr into that equilibrium and at those set concentrations? What happens? I'm going to shift. I'm now I put a stress here. I'm now shifting the reaction going this way.
Right.
Initially, until it forms a new equilibrium with new concentrations of this and this as a result of that.
Okay.
I could do that by changing the temperature. I could do that by increasing or by adding a catalyst. I add a catalyst that moves it this way. What's going to happen? My equilibrium is going to shift, and then what's that going to do to the Kc? It's going to lower it.
Right.
So those are all the things in play, and that's causing what you're seeing and interpreting as Kc.
As Kc values, can you say that anything between greater than 1 is more product, and between 0 and 1 is more reactant?
No, we're going to say something more. We're just going to take 10.
10, yeah, that
So
was
go
the.
10 both ways from 1, and it's at equilibrium. They're equal, we'll call it approximately. They're about the same. Anything more than 10 is favoring the product. Anything less than -10 would be favoring the reactant or something like that. You could say, or lower than
So
0.1
plus or
is what
minus
I should say. Not
Yeah, plus or minus
Yeah.
10, we'll consider it to be
Plus or
pretty,
minus
pretty
10.
similar, yeah.
Okay.
No, that's I should have said 0.1 instead of.
Yeah, like 10, yeah, like, yeah, it's like the next, yeah, so.
Okay.
Yeah, so just take that into consideration. So in this particular case, our products are heavily favored, right? So that's why we have a very large Kc value. Yeah.
Right.
Yeah. So this is an example of that. So in this particular case, this is like a Fenton test question, right? Yeah. What's the Kc? It's like a diagram. Yeah.
That's the one we just did.
Yeah, I know. I'm saying, but like, so this is like visually, right?
Yeah.
In this particular case, what you have, we said
That's
that the
true.
HBr is that red dot with the white dot with, right?
Yeah.
Okay.
And based off this diagram, we can see that there's a whole lot more of them than there is of the others, right?
All right.
Yeah, this is like Fenton 101, yeah. Yeah, so that just means that at equilibrium in this, in this particular case, it means I have more of HBr than I do of the others. Cool. Awesome. Yeah, products are favored at equilibrium. Significant, right? So then, in the reverse direction, what if my K is much smaller than 1, right? We said less than 10, right?
Right.
Cool. In this particular case, wow, very small, 10 to the minus 31, right? So if our exponent is that small, that means which side's favored?
Or reactants.
Yeah. Okay. Cool. And then just to recap our K expression, we would have NO with the power of 2 divided by those different molar concentrations of N2 and O2 as well.
Power of 1,
So
sorry.
don't lose track of that as well. Yeah.
Mhm.
So yeah, in this particular case, as we can see, the blue diatomic molecule and the red diatomic molecule represent the reactants.
Mhm.
So clearly in our diagram, we can see we have more of those than we do of the products in
Right.
this case, right? So if you prefer a visual, that's how we can see that as well.
Okay.
And this is at equilibrium, right?
Yes.
Cool.
Yeah, he just brought up a really interesting point. But keep this in context. These representations are at equilibrium. Those pictures are representing equilibrium, because if it wasn't at equilibrium, well, then you don't know what the K is. We'll
Yeah.
learn later a different type of K to try to figure out which side of equilibrium you're on.
Okay.
But these representations, before, you've never seen that. Everything was after the reaction was done.
Right.
So after all the reactants were used up. Now you're looking at a system that has both things in it. So presumably you're at equilibrium in those pictures and in all the diagrams that we're gonna see up to now.
Yeah.
What if you increase pressure?
So that's so he brought up a good point, right? What if I add some sort of stress
Right.
to the reaction, right?
That would be the P increase.
That's going to
That
be
changes the-
it's going to change everything, right? Yeah, you're
Oh, yeah,
changing the
the P and
conditions.
It may not.
Yeah.
The P
If,
and
yeah,
the
if we have a
It
bunch
may
of
not.
solids, yeah.
It would depend on the physical state.
Yeah.
Oh, sure.
If there are gases, it will change it because you'll change volume or other things. So you'll speed up the idea. If you keep volume constant, things are going to hit each other more often,
Right.
which is going to increase the rate of that direction for
And
the
the P and the
K
C,
of
right.
the kinetics, right?
Mhm.
So it depends.
Yeah. So what Dieter brought up is going to be presented later on in the chapter as Le Chatelier's principle.
Okay.
If I introduce some sort of stress, how does that affect my overall equilibrium? Will it go to the reverse or will it go forward? So,
Actually, we'll pop
yeah.
up even sooner. We'll get into gas phase equilibrium.
Oh,
That
nice.
just means that you have all of the
Yeah.
reactants and products in the gas phase. And now, things that are related to gases matter, like pressure. And so we'll come up there first.
Sweet. So yeah, like we said, if we have, approximately 10, in this case it says 1, right? It's going to mean that, yeah, so we have like a value of 3.93. That's a pretty reasonable number, right?
Mhm.
That would represent that at equilibrium, the concentrations of both sides are relatively similar. Yeah, not identical, but similar, yeah. Yeah, little squigglies, yeah. Neither products nor reactants are predominant. So an example. This is a good example too. I like this one. Yeah. So in equilibrium, constant shown below is 10. So what does that mean? That means that if I solved for Kc, right,
You get
which
10.
is products over reactants,
Right.
my value I got was 10, right? Yeah. So to reactor ratio, and it initially contains that. What statement is true, right? If I have a molar concentration of 1.1 on the left, and is that supposed to say 0.01 molar? I imagine, yeah. On your sheets, it's probably correct, yeah?
Mhm.
Yeah.
Just as
It says 0.01, yeah?
No,
Just-
0.0.
0. Okay, yeah.
What is, which one?
B,
Yeah,
0.
because this is the initial.
Yeah. Oh, 0, okay, got it. Yeah,
So-
initially, yes, yeah.
Yeah.
Because you're
Yeah.
forming B.
Yeah,
You
so,
haven't formed B yet.
so we said, this is actually kind of interesting because we said that 10, yeah, so, yeah.
That would be B.
Yeah. So what do you guys think? So if our K expression,
B.
yeah, represents It's that. So if A is that,
Yeah,
it's
B.
kind of interesting, yeah.
Oh, wait, not B.
So now
Yeah,
at
B.
time 0, you had just A, 1.1 molar. Now you've done something to initiate the reaction, and it's gone all the way to equilibrium over some time frame.
Right.
And you've now determined that your K
It's 10.
is 1. What is it?
10. Your K is 10.
Your
Yeah.
K is
Right.
10. So you look at your products over your reactants,
Right.
and what number would give you 10, and that will tell you which answer is correct.
B.
Yeah, so in which case, which of these, its products over reactants will yield an answer of 10?
Right. 1 divided by 0.1.
Yeah, so 1 divided by 0.1 in this case.
Right.
Be B, right? Yeah.
Mhm.
So yeah, get used to dividing by fractions, or divided by decimals.
So why was this a little tricky as opposed to everything we've gone through now?
It wasn't.
What was the hang up there? You're actually
You giving K?
Yeah.
Right.
Up to this point, everything has been intellectual. We've just developed the concept of what the K is and what's happening by looking at throwing out a number and saying this is large, small. Here you actually now you can realize you can put in numbers. You are going to have numbers for the concentrations. And when you do that, now you can determine different Ks. Or if you had the K, you could potentially determine concentrations. So now you have an equation that you can play with to make certain intellectual ideas come to light. Is this equilibrium going to favor the product or the reactant if you see the 10? If I start with these amounts and I end up with this, what do I end up with my K? And you could solve for K with those amounts. You just have to make sure you make the K right. In this case, the K is easy because there aren't any exponents, but when you have the exponents in there, it can become more complicated.
That's troublesome, yeah. So, in this particular case, yeah, if, let's say you don't fully understand it currently when we're going over it, write out the K expression, right? What would it be in this case? It'd be K, molar concentration of B over A, right?
Right.
Your next step would be to plug in the values that they give you, right? And which of those values results in a 10? If you do that, you're going to get B in this case, yeah? So that's just if you didn't quite get it initially, right? So. Manipulate. So yeah. Yeah, so if we modify a balanced chemical equation with an attached K, how do I change the K value? So it'll make a little more sense in this case, right? So meaning, let's say I have a reaction that already has a K value, an established K, and I reverse that reaction. What happens to the K value? So that would be A, right?
Yeah.
B would be, what if I multiplied all of the coefficients by some factor? Let's say 2, right? What do I do to my K value? Our C value? We're going to go over individually, don't worry. Yeah.
Oh.
Yeah, this is going over, yeah. Determining the overall reaction based off the sum of other ones. So let's say I had some sort of, mechanism, right? With individual K values. What can I do with those? Can I figure out the overall? Which is what we're going to do. So our first one, we said, what if I reverse it? So in this case, yeah, intuitively you can think, well, it would be, the inverse.
The inverse, right?
So let's say, for example, we have a simple equation like this, and a K value forward would be C over A and B.
Right.
Keep track of that. Exactly. Intuitively, if we reverse that guy, we're just going to get the inverse, right? 1 over that, which would result in flipping the denominator and numerator. In this case, we can see the reverse direction would be AB over C. Yeah. And keep track of the exponents as well. Don't lose track of that, right? Everything's the same. You're just putting 1 over your K value. Yeah, so we can see 1 over K forward is a way to do that. So.
Right.
Let's see our second option. Yeah, so let's say, what if we multiplied it by some factor? Right? So if we have A to B, the same reaction, then right, this is going to be our K expression. What if I doubled every coefficient? What happens to the K value?
Squared.
Everything gets multiplied by that, right? So I want you to almost imagine squaring the entire K expression,
Yeah.
right? Putting some parentheses around the entire thing and squaring it.
Right.
If you remember the rules of exponents,
Right. You multiply them.
you're going to multiply them, right?
Right.
Which is going to be presented here, like that. So all you're doing is if you multiply them by some factor, you're going to raise it to that factor. So let's say you triple it, or if you halved it, what would it be?
1 half. Square root.
Yeah, so you're going to manipulate it like you do in math class, right, at all times, right? So if you add some factor, multiply your expression by some factor, you're just going to raise your overall K to that factor.
Right.
Nothing's changing, right? We said if we reversed it, we're going to get the reciprocal of that. Yeah. Ah, that's good. So, yeah, I don't think it actually shows you. Yeah, so yeah. These guys work, right? Yeah, so imagine we're adding them, right? Yeah, so if we have, like, for example, we had 3 C's, right? So that would represent, right? So I can represent that as cubing it, right?
Right.
So I can represent that as C cubed, right? And if I square the overall thing, all I'm saying is that there's 6 of these lined up in a row. And I can represent that easier by just changing the coefficient to 6. Right? So imagine lining each of these guys up in a row, right? It's essentially, right, like you have x squared, you raise it to the 4th. What's my overall thing? It's bx to the 8th.
But you're essentially just increasing the concentration.
I'm sorry?
You're increasing the concentration, doubling the concentration, right?
Yeah, so, or in this case, yeah, it's more like I'm affecting, yeah, like the molar ratio.
Right.
Can you square the k directly? Let's say if the k is 10, you do 10 squared.
In this case, yeah, I believe you can, right? Yeah, if you multiply them by 2, then yeah, because what does that mean? This whole expression represents this k. So why not substitute, right?
Right.
Yeah,
Did
plug
you
in the
say
k.
multiply it by 2?
No, square, yeah, so if this whole expression represents this k, if I square this, it's the same thing as squaring this.
Right. If you have the K already.
Yeah.
Mhm.
It's a good question, yeah.
Square.
Yep, square both.
Or cube or whatever else, whatever number you're multiplying through, but you're initiating that through the equation here, right? So if you have a greater ratio that you find, or that you want to say I have a certain amount, and I now double everything in my container, then you double this, you just square it, and then you square the k.
Cool.
And that's all you do. Whatever you do to one side, you do to the other, just like any mathematical.
So that's a different equilibrium.
Yeah, exponents, logs,
It's a quick
everything,
way
right?
to
Yeah.
determine k without actually
Yeah.
unfolding it all,
Right.
right? These are just ways to manipulate k. So if you understand the details of what you're manipulating, you're actually manipulating the reactants and the products in how they represent k. And you could just do that directly to k, as opposed to going through, let's
Each
say I
one of them.
assign C is 0.5 molar, A is 1.2 molar, and B is 3.4 molar. Instead of plugging all that in, I just simply double k, or square k.
Right.
Right, it's just easier.
Sometimes you're going to be given some values, like what if you didn't have the individual concentrations and you just had k? Square k. Yeah. Yeah.
But if you did have the individual concentrations, then you could do it all longhand if you like.
For sure, yeah, absolutely.
Right?
Yeah. So we
You
have
don't have to.
one more different type of manipulating the concentration. We're off at 25, right?
Yeah.
So it's going to line up perfect. So we'll add this one, yeah. Yeah. So there we go. K squared in that case. Yeah. Example 1. Cool. This is a really great question. So let's say we have an established K, right, for the top reaction, right? And that value is 0.01. What would be my new K expression for this?
Square root?
Or better yet, what did I do to this reaction before I even started doing any math?
Oh, you have it.
Well, B is now in the place of A. So I'm going to get the inverse then, right? Because I've reversed the reaction.
Right.
So then, if I'm getting the inverse. And what about the coefficients?
Halved it? Divided by 2?
We've halved it, so what do we do for the power? We raise it to, we square root it, yeah. We square, yeah. So you can see?
Square root.
What would be my equilibrium constant? So it doesn't actually work this out for you. So I encourage you to write out the K expression, right?
Right.
We said, and do it as a stepwise process. My K would be reversed, which would be putting 1 over my 0.01, right? And if I'm dividing everything by a factor of 2, I'm going to square root all of them. Right? So if you plug that in, what's the value you get? You should get 10. Which in this case, it doesn't actually tell you. Yeah. Yeah, 10 is going to be the right answer. And if any of you guys have an issue calculating things, putting like fractions with square roots, you should definitely bring it up after the class, and we can show you how to do that. Because you're going to be doing that quite often. Yeah? Your calculator is going to be your best friend from this point on. Right? We have one different type of stress we can apply. Yeah.
So it would be the expression uses just k equals 1 per 1 over 0.00?
Exactly, yeah. So what Dieter said, when you're writing your k expression in that previous problem, you should have got 1 over the square root of 0.01.
Okay.
Plug that in, you should get 10.
You could also just write it to the value of 0.5.
Yeah, that too.
I like that.
You like prefer that? Yeah.
Only because it's not always going to be square. It could be, 0.25 or whatever.
Yeah, be like 1/3 or something. Yeah, yeah.
We used to do it that way.
Yeah. Okay. So we can also add up a series of equations. You guys were familiar with this with mechanisms, right? So
No.
we just went over this, right? So if I'm adding a series of equations together, I'm going to multiply their k values. We're not going to add them. We're going to multiply them together. We're going to get an example of what it would look like right now.
Okay.
Yeah. Let's say we have two different equations, right?
Okay.
And an overall equation, right? If you wanted to solve for the overall k, from the previous slide, we're going to multiply the corresponding k's. So k1 and times k2. And we'll get the overall. So, okay. Does that make sense for everybody? So what's the worst case scenario? What if they're flipped, right? What if it's flipped by some, it's flipped and multiplied by some factor, right? You're good? Yeah, it's almost like Hess's law in a way. Yeah, if you can kind of relate it to Hess's law in a way, right? Moving them around, flipping them in the necessary way, right? So if I were giving you a hard question, I'd probably flip that and multiply it by some factor as well, right? To make you use all of the rules we just covered, right?
Right.
Yeah. So in this particular case, see, you can see those guys cancel like that. Very familiar. You guys should be very familiar with the canceling these guys out. K3 value would be simply just be multiplying K1 times K2. Cool. Yeah. There we go. Yeah. So let's see. Summarizing. Yeah. So if you wanted if you're more mathematical, you might be able to actually see this. If you prefer to see this like this, K1 times K2. You can multiply them by that. And you can see that CH4 is found on top and bottom, so it'll cancel, right? As well as any coefficients will be reduced as well. So let's see. See the power of 4 there is removed. And you solve for your K3. Cool. Let's get an example. You had a question, Minerva? Yeah. Yeah. Do you want me to go back? This guy? Cool. Yeah. Yeah, I believe on one of your, at the exit tickets you guys get one that's flipped. Yeah, so look out for that. Yeah.
Oh, okay, that's the addition. Got it.
Yep.
I thought it was
Good.
3.
Yep.
So if you have to, you're gonna do division.
Cool.
All right, there we have K1, K2. It's a simple example. Two equilibrium constants. Okay. So this is kind of like what I was talking about. We'll finish it up with this, right? Well, in this case, check it out. So it's almost exactly like Hess's law, right? Like we said. We're trying to get this K1 up here. How can we manipulate these bottom two equations to look like the top equation?
We can write it out and just divide them.
Right,
Yeah.
so yeah, I'd encourage you guys to see that, right? So notice
We have
that
to flip
CO2,
it. We have to flip this, the green
yeah,
one.
CO2 is found on the left side here.
Right,
And the only equation that contains CO2 is this center one.
right.
We'd have to flip it.
Uh-huh.
And if we flip it, we do what to the K value? You get the reciprocal.
Right.
Okay, that's our first step. And if we flip that, how many H's will I have on the left side?
You're gonna have just one?
Well,
Oh, actually 4.
I'd have an H here, right?
Uh-huh. And then
have
the other
another
one
one there.
3 of them. Yeah.
Does that correspond to the number of H's I need?
Absolutely.
It does, right?
The
So that
COs
means our H's are good, our
COs
CO2s are good,
COs cancel out.
our H2O would be flipped over here, which is where it's found on the products over there. And we have our CH3OH as well.
And the COs cancels out.
So we see that. Boom. I know, yeah.
Wait,
So it didn't flip it?
So
It did flip
this
it,
is
yeah.
just supposed to represent, this is the overall equation. And K3 should equal K1 times K2. You're missing K1.
Yeah.
So that's here. So now you're solving for K1.
Right.
So K1 should be isolated, K3 divided by K2 is what you should have here. So this is K3, this is K2, these are just not written properly.
Yeah, is that
And
what,
then
is
like that.
that's, okay, so yeah, that's, disregard the
That's
slide.
how I did it.
You just,
Oh.
K3 is equal to K1 times K2, that's it. You're solving for K1, so K3 divided
Yeah.
by K2 gives you K1.
Yeah.
Algebraically speaking, yeah.
Shouldn't
What are you
K,
talking about when you're saying?
1 equal 2 equals K3 over K2?
Say, like,
You're not switching
if you
anything.
don't know these
You
adductive
simply have the overall equation is equal to the.
It's interesting, yeah, because when we flipped it,
Yeah.
we got the reciprocal, right? Did we not? Yeah.
What they did is they
Yeah.
added the first two.
They did them
To get
in a
the
different
third
way.
one,
Yeah.
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 So you're saying
Yeah.
if we don't have.
Yeah, you can do it in either way. Yeah.
Yeah.
The top one is
So
the
like,
K
if you
that we're
didn't
trying to
know
find,
that the equation.
but it's
So
all
if you
based
didn't
on
know that,
the
if you
bottom.
add these
The bottom is zero.
you might have to take out the equation and flip it around. But because they don't.
Okay, so we'll pick this one up on Thursday. Have a good couple days, and I'll see you on Thursday. And at that point, we'll talk about the exam.
Question, Nate?
Thank you, Nate.
It's what they did here was all they're doing is
Bye, my friend.
¿Cómo?